right, so the first problem up here, we should be able to solve. It should look a lot like what we just did on your weekly review. So just remember, if you're solving something, factoring is the only real method that we have that can kind of transfer over from quadratics to higher level things. So when I look at example 1, I want to factor it. And in order to factor, you need to have everything on one side set equal to 0. So I would add 21x squared to both sides so it looks like this. Okay. So steps again. What should I look for first? Connor? Good, GCF. So here 3 goes into everything, and they all have at least an x squared power of x. So I would factor out 3x squared. All right, so then after this, the part that's left to continue factoring is a quadratic. I've already taken out the GCF. If I've done that correctly, there's no more GCF to take out, right? It's not a perfect square pattern, so I would try to factor it my trinomial factoring idea. So either guess and check, or you guys would use like the x. Is there anything that multiplies to make 7 and adds to make -4? No. That means that's not factorable. But it is a quadratic. So when we go to solve this, our first factor is 3x squared. Our second factor is this quadratic that we can't factor any further. When we set 3x squared equal to 0, we're going to get x equals 0, right? And then just quick side questions here. What would be the multiplicity of that solution? 2. What would that mean about that point on the graph? It would be a turning point as well as a 0. Okay? All right, the second part, we know it doesn't factor because we tried to factor it and it didn't go any further, but it's a quadratic now. So now that it's not something higher degree than 2 and we're back to a quadratic, if it doesn't factor, what are our options for solving? Quadratic formula or completing the square, okay? If we use quadratic formula, b squared minus 4ac. It looks like this. And so a small reminder about how to simplify this stuff, and a note for you guys. Quadratics are part of polynomials, so though this is a new unit, you're going to see quadratic stuff all over it. You're going to see quadratic stuff all over your weekly review, and you should expect quadratic stuff intermingled on your next test with all of this stuff. Okay? So in the radical, 4 times 7 is 28. 16 minus 28 is -12. And then how do we simplify that -12 inside the radical? Okay, so a 2 can come outside the radical and a 3 stays in. And then because of the negative, I. And then each term in the numerator has a factor of 2, and so does the denominator, so we can reduce it, and this will be 2 plus or minus I rad 3. Okay? Because it didn't specify for real answers, I would include all the answers here. So I have 0 as well as these complex solutions. If you were graphing this, how many times would your graph show it hitting the x-axis? 1. Okay? Just at 0. Though we have these other solutions that are complex, those are not real numbers, so they wouldn't be seen on the x-axis of the graph. Okay? All right. The next thing we're going to talk about is the new special pattern. Are you guys okay? Yeah? All right. So first I want to remind you of your old special pattern. I'll slide it back over in a minute. So we just factored, say, like x squared minus 4 a minute ago. And then we quickly factored it as x minus 2 and x plus 2. Okay? So we keep talking about this being a special pattern, a difference of squares that you're supposed to have memorized. That's because x times x is making the x squared, and then you're getting these middle terms that are working out to be exactly the same thing with opposite signs that cancel each other out, leaving you with just the highest degree and the constant. Today we want to do the same thing, but we want it with perfect cubes, okay? So for example, x cubed minus 8, those are both perfect cubes. They actually factor, okay, into something. But when you look at the factors and what you're going to multiply together, what you would need to get is you'd need to get an x cubed at the beginning and an 8 at the end. And what would happen in between is that the terms with x squareds would have to cancel out and the terms with x would have to cancel out, okay? So it's a little more complicated than our perfect square pattern because of the cubing. So here's what they look like. First of all, if you factor a sum of cubes, it means you have something cubed plus another thing cubed. They might not always look like this. Things that could be sum of cubes. X cubed plus 64. X cubed is x being cubed. 64 is 4 being cubed, okay? It could look like 8x cubed plus 27. 8x cubed is really 2x being cubed, and 27 is really 3 being cubed. So what we're saying is that it won't look exactly like this to begin with, but both terms that you have are perfect cubes, okay? If that's the case, here's how they factor, and difference just means there's subtraction between them. Notice this time that you can do both, but when we factor our difference of squares, we only do it when there's a difference, okay? That's because when it's squares, I'm going to scroll back over and I'll be back in a minute. When it's squares like we were looking at right here, in order to get these two middle terms to cancel, you have to have one positive and one negative, which forces this 4 here to be negative. So we can only factor x squared minus 4. If it was x squared plus 4, it wouldn't work because the middle terms wouldn't cancel. But just like with odd powers, like if you're taking the cube root of something, it's okay for it to be negative. If you raise something to an odd power, it can turn out negative or positive. That's why you can have both sets of patterns here, because that power of 3 keeps more of the number's identity, like negatives or positives, than when we square things, okay? So here's how they look. If you have something cubed plus another thing cubed, here's how they will factor. So we're first going to write down the pattern and then we'll try to understand it. I'll show you some tricks people use. I'm not big into tricks, but lucky for you guys, other teachers are really good at tricks. And the difference looks almost the same. There's just a couple of sign changes. Okay. So before we develop our tricks, just over here in the why it works, I'm just going to show you this one for a second. Notice that if you did multiply this out, a times a squared would make your a cubed. The a times the ab is a negative a to the second power and then b to the first power. And then the a times the b squared is positive and it's a to the first power, b to the second power. But then what happens when you take through the b? So the b times the a squared makes a positive a to the second power b. See how these ones match? And one's positive and one's negative. So guess what happens to them? They cancel out. Then when b multiplies the ab, that would be a negative a to the first power, b to the second power. Notice that these terms match, but one's positive and one's negative. So yet again, they would cancel out. And then b times b squared would make b cubed, and you're left with your a cubed plus your b cubed. The other one would work exactly the same way, okay? You would have a cubed at the beginning and you'd have a negative b cubed at the end, but it would be just the right amount of signs so that all the things that worked out to have the same powers of a and b cancel each other out. Is that okay with everybody how this works? All right, so we want to know these patterns. So first of all, notice I don't really memorize this as two patterns, but if you guys haven't learned this about me yet, you will. I'm not a big memorizer, right? I feel like my brain doesn't have space or something. So when I see cubes, okay, I do the signs separate than the numbers. So first, like we said over here, if you had 8x cubed plus 27, it's really a 2x that's being cubed and a 3. The 2x and the 3 are like your a and your b, okay? So when I see my perfect cubes, I know that those are the things I'm going to use in the factors, like the cube roots of them, the things that are being cubed, okay? A and B, okay? This starts with A, ends with B, to the higher powers, and the middle has them multiplied together, okay? So that's just kind of how I look at it. I just find my A and B, so to speak. I know which numbers to use. The beginning is at the beginning here and the beginning here, but just squared. The end is at the end here, but at the end here, just squared. And I know this one's supposed to be 3 terms, and I multiply the 2 things together in the middle. Okay? That's the same pattern here that's here. But then look at the signs. Okay? Notice when it's a sum that you're factoring, that first binomial factor is also a sum. When it's a difference that you're factoring, the first binomial factor is also a difference. And then notice these are opposites. So if you're using a difference here, you're using a sum here. If you're using a sum here, you have to use a difference here. Why do we have to do that? We got to get all the stuff to cancel out, right? So if you're using the plus here, you need the minus here. If you're using the minus here, you need the plus here. And this last term is always a positive term. Okay? So you can memorize that how you want. The only trick I have for you that teachers have come up with, I'm sure they stole it from someone else, is the word soap. I'm really not into tricks, but you guys will probably like it. And all it is about the signs. This one's a minus, right? Same, S. Opposite, O. Always positive, AP. Soap, S-O-A-P. I don't know. There you go. All right. It's the best I've got for you. It's the only thing people have. You can go look on that beautiful thing they call the internet, see if people have other great ways for you to remember it. Okay. That's about it. All right. So how would we use it? If you look at example 2, see how it says 2x cubed equals negative 54, and we're supposed to solve it. Now, you could divide this by 2 and cube root it. If you did that, how many answers would you get? 54 divided by 2 is 27. And then you would take the cube root of negative 27 and you would get negative 3 as your answer. You'd get one answer. There is only one real answer to this problem. But you're missing the other 2 solutions because it's a cubic, right? So it can have 3 maximum solutions. One is real, and you can find it very simply using cube roots. The other 2 are going to be complex, and you can't find them that way, okay? So in order to get all of the solutions of this, what we would do is we would rewrite it so that it was set up on one side equal to 0. And then we would want to go through and we would want to factor it. Now, because it is set equal to 0 and these are both divisible by 2, I would want to divide everything by 2 right away and make smaller numbers. Okay. Now, when you go to factor this, you go through your process. Greatest common factor. Well, we kind of already canceled it out because we divided both sides by 2, right? Next thing is special patterns. Notice all of our special patterns just have 2 terms. They're either perfect squares with a minus sign between them or perfect cubes, and they could have a plus or a minus. Are these both perfect cubes? X cubed is a perfect cube. 27 is a perfect cube. So then you got to think about what's making those perfect cubes. So in other words, when I think about this x cubed, it's made by x being cubed. When I think about 27, what makes 27 when it's cubed? 3. The x and the 3 are what I'm going to use in my factors, and then I would have that factoring pattern memorized, okay? So I know that I would use x and 3 in the binomial, and then that there's a trinomial, so a bigger one, that x is used here, but it's squared, and 3 is used here, but it's squared. And how do I get the middle term of this trinomial? Multiply them together. So x times 3 makes 3x. And then I have to deal with what signs are everything. I was factoring a sum, so the first factor is plus. Then in this sign, I'll have a minus so that things will cancel out. And the last sign is positive, okay? So I have x plus 3 being multiplied by x squared minus 3x plus 9, if I simplify that 3 squared. Okay. And then this is like the first example we did now. I can't factor this second part. This quadratic, there aren't 2 things that multiply to make 9 and add up to make negative 3. So I'm going to take my first factor, x plus 3, and set it equal to 0. That gives me the same solution you would have got if you just solved it right off the bat using radicals. Okay. The solutions you wouldn't got are contained here, That's right. You wouldn't have got them. Okay, you wouldn't have got are contained right here in this quadratic. Okay, and we can't factor it, so we would move on to one of our other methods. And now that that part's just a quadratic, we could use the quadratic formula just on this piece. So x equals negative b plus or minus square root. So b squared minus 4 times a times c all over 2a. So inside the radical, we have 9 minus 36. So that's like negative 27. And how does the square root of negative 27 simplify? So there's a negative. So what does that have to do? Pi. 27 is 9 times 3. So the square root of 9, it means a 3 outside and a 3 left inside for the other factor of 3. Okay, so we have one real solution, but 3 total solutions for this cubic. Our real solution is negative 3, but we also have these 2 complex solutions. Any questions about using our new factoring pattern? Jake?
So if we were to graph this, what would the graph look like? Would it only go through negative 3?
Yeah, and so it would still have those loops of a cubic, and I don't know if I'm drawing them in the right spot right now. I'd have to test some other things. Well, actually, I can tell you this. So it goes through negative 3, right? The y-intercept is 54, so it'd be way up on the y-axis. So what's maybe happening is something like this, and it's doing those loops. It's just doing them at a place where they're not all coming back and crossing through the x-axis. And that's why it has complex solutions, because there are places where it's turning around and it's making all those curves that we want, but they're not down here where they'd hit the real number axis. Okay?
They just gave you the equation.
Uh-huh.
How would you know that it went through 3 times? Because it doesn't have, like, say it has a specific 3.
So if you would have to either factor it out or see if you want to know if it has a multiplicity of 3. By factoring it out right here, we see that that x plus 3 factor only has a multiplicity of 1. And that's how I know the other terms take place somewhere else, and it still just crosses through that normally. Because remember, the degree only tells you the maximum number of solutions. It doesn't give you the exact idea. And that's why when we do graph the ones we're graphing, we're sketching, because we're just getting it right in shape and zeros. We don't really know anything else. I know that these, I mean, technically, these curves could be down here, and then it could cross through 3, and then it could cross through 54. Those, so you could draw it both those ways, and those would be acceptable sketches of this graph because there's so much unknown information. Okay, and so you would know based on the degree of that factor being only 1, that it would just cross through, and that the other solutions are complex, so it does curve, but not back through the x-axis. Okay, whereas like the one we graphed in the weekly review, if you added up all the multiplicities of the zeros, they added up to the total degree of the function. So it wasn't curving anywhere else because those met all of the requirements for the maximum amount of zeros. Okay. All right, we're not going to do the calculator portion. Okay. You guys are good with your calculator from what I'm gathering, right? Just entering it in and finding zeros, maximums, and minimums. So since we kind of discussed that a little bit, we're going to leave that. And then we're just going to do this one word problem. Okay. All right, so this word problem says we might have to use our calculator to help us solve it. It just depends on if we get something factorable or not. So it says, what are 3 consecutive even integers whose product is 4 times their sum? Okay, so first setup. What are we trying to find? 3 consecutive even integers. So let's say we called the first one x. Fair enough? What would the next one be called if these are 3 consecutive even integers? Ethan? Are you guys on board with Ethan? So if you picked 2, the next one is 4. It's the number before plus 2 more. So the second integer would have to be the first one plus 2. I don't want to put a new variable in the equation if I don't have to, because I don't want like x, y's, and z's multiplying each other. That means my best shot at solving is like a system of 3 equations with 3 unknowns. I don't even have 3 equations to write here. So what would be the next number? Mary? Good, x plus 4. Is this okay with everybody? So 3 consecutive even integers. What if they said 3 consecutive odd integers? Would this still work?
No. Yes.
Yeah, it totally would. Because x would just be an odd number, and then the next number would still be 2 away from it, and the next one would still be 4 away from it, right? What if it just said 3 consecutive integers? How would this change? Cooper?
It would be x plus 1 and x plus 2 as other ones.
Are you guys okay with that? So if it was just consecutive integers, it'd be x, x plus 1, x plus 2. So these aren't here because of even, right? These are here because even numbers are spaced 2 apart, but odd numbers are spaced 2 apart as well. So whether this question was about even or odd integers, this setup for the variables would work. Is that okay with everybody? All right. And then it says their product is 4 times their sum. So is telling me whatever's over here is going to be equal to whatever's over here. So product means all of them multiplying each other. So if x multiplies the x plus 2 and that multiplies the x plus 4, that's the product. That's supposed to be equal to 4 times their sum. The sum would be all of them added together. So x added with x plus 2 added with x plus 4. Is everybody okay with my interpretation mathematically of what the words were saying up there once I defined my variables? Okay, so this looks disgusting, so we're going to try and clean it up a little bit. We're going to have to expand it out because though this looks factored and we're like, yay, we can only factor things if they're set equal to 0, which means all the like terms would have to be combined. So we're going to have to multiply this out and simplify this and then bring everything to one side. So x plus 2 times x plus 4 would give us x squared plus 6x plus 8. And then over here, I'm just going to combine together these like terms. I have 3x plus 6 in there. Okay. Now I'm going to distribute on both sides, and then I'll move things around to combine like terms. So on the left side, I'd have x cubed plus 6x squared plus 8x. And on the right side, 12x plus 24. And now I want it set equal to 0 so I can actually try to factor it. So I'm going to cancel out the 12x and the 24 so that I have a 0 on one side and all my other terms on the other side. Pause for a minute to make sure we're okay with the manipulation that I did to this equation. So is everybody okay that I just multiplied stuff out on this side, combined like terms and multiplied on this side, and then brought everything to the same side and combined like terms? Is this okay? All right, so now to solve this to get the zeros, it's a degree higher than a quadratic, so I don't have completing the square, quadratic formula, and factoring as choices. I only have factoring as a choice. When we look at this, our first option when factoring would be take out the greatest common factor. Is there any greatest common factor? No. Okay. Next option is it a special pattern? So that used to mean, is it 2 squares with a minus sign between them? No. It now means, is it that, or is it 2 perfect cubes with a minus or a plus between them? No, this is much longer than anything that we see with our special patterns, right? Third factoring option is specifically for quadratic factoring, our guess and check or our little x problem. We can't do that because it's a cubic, but it does have an even number of terms. So our only option here, if it's factorable at all, is grouping. At that point, if it wasn't factorable, we're going to see if this one is in a minute. If it wasn't factorable, then your only idea here, as far as our expectation, would be to use technology, and you'd graph it, and you'd see where it's crossing the axis, okay? And then once you find that 0, you'll be able to figure out your solutions. We're going to test it and see if it's factorable. The numbers look pretty friendly, like it might be. So we're going to go through and see. If I group it and group together these two, x squared is the greatest common factor, leaving x plus 6. And if I group together these two, negative 4 is the greatest common factor, leaving x plus 6. So this is looking factorable, right? Because I factored it, okay? And so this gives me x plus 6 times x squared minus 4. And I can actually factor that even further, right? The x squared minus 4 is perfect squares. So this is x plus 6 times x minus 2 times x plus 2 equals 0. All right? So what are my x values that make this equation true or equal to 0? Sammy?
2, -2, -6.
Good. Are we all on board with Sammy? So there's actually 3 possible solutions to this problem. These aren't the 3 numbers that are added together because all 3 of these numbers are supposed to be for x. So when you look back at what just happened, you just found 3 options for the starting points of this sequence of integers. So the sequence of integers could be 2, and what comes after 2 would be 4 and then 6. Or the sequence of integers could start with -2, and what comes after that would be 0 and then 2. Or it could start with -6, and what comes after that would be -4 and then -2. All 3 of these supposedly solve this problem, and if you felt like they were lying, then you would just go back and check if it works. Does their product equal 4 times their sum? So, product of these, 6 times 4 is 24, times 2 is 48. 6 plus 4 is 10, plus 2 is 12. 12 times 4 is 48. Okay? Sum, 2 plus 0 plus -2. 0. Okay? 4 times that, 0. Product, 0. Now, some people might argue with you that 0 is not an even integer. By the definition of evens and odds, we're not going to debate it. We could go on forever, okay? But you could get that argument at a higher level. All right, -6, -4, -2. If we multiply them all together, -6 times -4, 24 times -2 is -48, okay? If we add them all together, -12 times 4 is -48. So they actually all meet those requirements. So all of those possibilities would work, okay? There are some like this in the homework. I want to point out again, we got really lucky at this step right here because when we factored, they actually factored really well. If they didn't factor really well, I have no expectation that there's some secret thing in your back pocket you're supposed to know that solves this problem. If it doesn't factor, we would rely on technology. Have I made that perfectly clear? So if you're doing this homework assignment, there are problems like this about consecutive integers. If you get to a point and it's not factorable by grouping, what is my expectation that you'll do? Take out your calculator, and how will you find the solution on the calculator? You'll plug it into the y equals and graph it, and then you'll look for the zeros, and you'll use the calculator to calculate the zeros. You'll find them. They should be whole numbers if they're talking about integers, positive or negative. Okay, it was just not something you could find by factoring. Is that okay with everybody? All right, so not really a whole lot of new idea today, just one giant new thing that you have to look at. What's the giant new thing we have to look at? Factoring perfect cubes. This is really, in my opinion, I'm not saying none of this stuff is difficult or didn't need review, but this is the main idea. Otherwise, did we already know we could factor and solve stuff? Yes. Did we already know quadratic formula? Yes. Have you already done algebra word problems at different levels? Yes. But the main idea here is adding in this cubic factoring problem and then reviewing how all these pieces kind of fit together. All right? This is okay with everybody? So this goes with skill 5. Skill 5 is going to be knowing that new factoring pattern. Okay?